You know, when you watch a rocket launch, that unbelievable pillar of fire, the roar that you feel in your chest, it's just one of the most powerful things we can create. But here's the thing, what you're really seeing is an explosion, a massive, violent chemical reaction that is somehow, against all odds, completely under control. So every single time one of these rockets clears the tower, it's this incredible victory of precision over pure chaos. I mean, we're talking about engineers who take a material that is literally designed to release a mind-boggling amount of energy in an instant, and they tame it. They channel all that explosive force into doing something useful. And that right there is the big question, isn't it? How on earth do you engineer safety and reliability into a system when its main component is, well, basically an explosive? Okay, let's get into it. To figure out how to control this stuff, you first got to understand what it is. And at its core, solid rocket fuel is, without a doubt, a type of explosive. Let's just look at NASA's own definition here. They call propellants high-energy materials that decompose exothermically, which is just a fancy way of saying they burn and release a ton of heat. The key part, though, is that they do it super fast to create this immense gas pressure. That pressure is what shoves a rocket into the sky. But read that definition again. It sounds an awful lot like the definition of a bomb, doesn't it? So when this material goes off, the reaction is called explosive decomposition. It's this chain reaction that can go a couple of different ways. It all starts with initiation, the spark. From there, it can either deflagrate, which is a really, really fast burn, or it can transition into something way more violent, a detonation. And this right here, this is the single most critical difference in all of rocketry. Deflagration is what you want. It's the reaction moving slower than the speed of sound. Think of it as a controlled, incredibly fast whoosh. Detonation, on the other hand, is the absolute nightmare scenario. It's a shockwave ripping through the fuel at supersonic speeds. It's a bang. The entire job of a rocket engineer is to make sure you get the whoosh and never, ever the bang. Okay, so if you've got this material that can either burn really fast or just straight up explode, how do you know which one it's going to do? Well, you have to test it. And I mean, you test it brutally. You have to turn all that potential chaos into cold, hard data. So this is a page from a Department of Defense manual, and it shows exactly how engineers find a propellant's breaking point. Check out the detonation test. The procedure is, well, it's shockingly direct. You take a big chunk of the propellant, you stick a military-grade blasting cap right on it, and you set it off. You are intentionally trying to make it detonate just to see if it's even possible. And that's just one test in a whole series of abuse they put this stuff through. They try to blow it up, they drop heavy weights on it to see if it's sensitive to being hit, they light it on fire out in the open just to see how it behaves. They even bake it in an oven for 2 straight days to see if it'll deform or just ignite on its own. Only if it survives all of that can it be considered safe enough to even handle. All right, so you've managed to create a propellant that's passed all the brutal tests. Now you have to actually turn it from a raw chemical into a perfectly formed, totally stable rocket motor. And this is where the challenge shifts from chemistry to a level of precision engineering that is just mind-blowing. So before it hardens, the propellant is this thick, goopy slurry. The best way to think about it is like the world's most dangerous cake batter. The technical term is propellant processability. Basically, how well can you mix it and pour it? The problem is, the thicker and stickier it is, the more likely you are to get tiny flaws, like air bubbles or cracks. And in a rocket motor, any flaw, no matter how small, can be a fatal one. The level of detail here is just staggering. To make sure that gooey propellant sticks perfectly to the motor's insulation so there are no gaps for fire to creep into, they use something called a powder embedment process. They put down adhesive and then they spray tiny little granules of powder into it. This creates this perfect, rough surface for the propellant to grab onto. It's an insanely precise step, all just to guarantee a flawless bond. But even with all of that painstaking care, you can't just assume it's perfect. So after the motor is built, they scan it. They hit it with powerful X-rays and ultrasonic scanners to hunt for any hidden defects inside. And we're talking about looking for cracks that are just several dozen micrometers wide, that is smaller than the width of a human hair. Because a flaw that tiny, if it's in the wrong place, can cause the entire motor to fail catastrophically at ignition. And this brings us to a really sobering part of rocket science. To build a system that actually works, you have to spend a huge amount of your time thinking about how it could fail. You have to game out the absolute worst-case scenario. Because the stakes, Well, they couldn't be higher. You've got human lives, you've got billion-dollar spacecraft, the whole thing is on the line. So to stop a disaster from happening, you have to do something that sounds a little backwards. You have to calculate it first. You have to model it, quantify it, and understand it completely. This chart might just look like a bunch of boring data points, but this is a life-saving tool. What NASA did was plot the maximum distance that burning chunks of rocket were thrown during actual failures, from rockets like the Titan and the Minuteman. They used this exact data to figure out the safe distance for buildings and, for people. This is literally a map of past destruction being used to create future safety zones. And these failures, they are not just theoretical exercises. They really happen. Back in 1971, a truck carrying a rejected Polaris motor crashed. The fire from the crash caused the motor to have what's called a low-order detonation. It wasn't a full-blown explosion, but it was still a violent failure that shattered the motor casing. It's just a constant reminder that the danger is always there, and you have to manage it at every single step. So how do engineers actually put a number on that danger? Well, one of the key tools they use is TNT equivalency. They calculate the absolute worst-case explosive power of a propellant and then express it as if it were a certain amount of TNT. This lets them use all the existing data on explosions to predict blast waves, debris, and all the other hazards, which then helps them write every single safety rule. So let's kind of bring this all together. You've got a propellant that's been carefully designed, brutally tested, manufactured with microscopic precision, and has had all of its failure modes calculated down to the decimal point. All of those pieces become part of this massive, comprehensive system that is designed for one thing, and one thing only: safety. And a core idea in that system is something called the 3-failure rule. For something truly catastrophic to happen, like, say, the main engine firing by accident, the system is designed so that it would take at least 3 separate, independent failures for that to occur. Not one thing going wrong, not 2, but 3 things have to fail. It's layer after layer of redundancy. This diagram for the space shuttle, just look at it. Don't even try to read the boxes, just take in the complexity. Every single one of those arrows and boxes is a procedure, a check, a verification, a sign-off. It's this enormous, intricate ballet of safety procedures, all designed to catch any possible failure long before it has a chance to become a disaster. It's really an incredible system. And it kind of leaves you with this one last thought. When you're working in a field where success is measured in micrometers inside a solid fuel grain, and failure is measured in the megaton equivalent of TNT, the science, the engineering, and just the sheer human diligence that's required, it's almost impossible to comprehend. And that is what it truly takes to tame an inferno and to reach for the stars.